All right, so let's do this. So you just saw, if you're watching what I just did, that was my first time where I click on the slides and they didn't exist, so I had to fix them real quick. That's why I like to download the slides off the website, make sure I didn't mess anything up, and I messed something up today, so I was able to fix it real quick. And something's still broken here. There we go. So we should have slides now. Hey, there we go. I don't remember if I mentioned this last time, but homework 1 is out. So let's talk about it very briefly. I'll keep revisiting it as we cover more content, but I like giving a roadmap of where we are with the homework. So after today, you'll be able to do Learning Objective 1. You'll have everything that you need for Learning Objective 1, and a little bit of what you'll need for Learning Objective 2. We won't quite get all of it until Wednesday, but Learning Objective 1 you'll be able to do. You won't be able to do the Docker setup stuff until next week, the week after, week 3. I don't remember. I think week 3. But you'll be able to start doing the objectives without Docker before you get to that, get to the Docker setup stuff. But Learning Objective 1 is on the table after today's lecture. All right, so let's do these slides and talk about stuff. HTTP. We're getting into it. So a quick reminder, I'm watching the... Hi, Trevor. I'm watching the lecture channel on Discord. So if you see me talking to my phone, that's what's going on there. If you have questions, feel free to put them there, or do the old-fashioned raise your hand and ask a question. That always works perfectly fine as well. So before we get into content, anybody have questions? I think we're pretty on track right now. I think we got how the grading structure works out there. We know how the internet works. We're ready for HTTP. But if not, y'all have questions? Yeah.
I just saw that we have lecture recordings on the YouTube page from last semester. We have it for this semester too.
Yes. So I haven't talked to the TA to make sure to get all the logistics worked out for him to upload YouTube this semester. But once we do, he'll start uploading them for this semester as well. They are on UB Learns right now. If you want to go to Panopto, the recordings, it's automatically through the room, and it's usually uploaded like minutes after lecture ends. They'll be up on Panopto that you can get through UB Learns. There should be a classroom recordings link and everything. But we will get them re-uploaded to YouTube as well. Yep. All right. Anything else? Anybody want to ask about recitations again? I keep getting that question. Every semester it happens, but where are recitations? Do we have recitations this week? There are no recitations, if anybody is wondering and doesn't want to ask now. No recitations. They're replaced with your group meetings, which will start week 5. So nothing you got to worry about for a while. All right, HTTP overview. What is HTTP? Well, let's take a look at where we are, where we came so far. We only had one lecture, but we actually covered a lot of ground very quickly and at a high level. We didn't get into detail with any of it really. But this is everything we covered. We have the physical internet, that there are actual big cables. As humans, we wrap the entire planet with these massive cables, and that's how we're connected to each other, is through all those cables. With very little wireless technology, a surprisingly small amount of wireless technology. Even though that's how we interact with everything. To us, it seems like everything's Wi-Fi, but the internet at large, it's not really how it works. It's all cables. Then we had the Internet Protocol, which defined how to send packets through those wires. I'm saying wires again. You know what I mean. But the Internet Protocol to figure out how to use those cables to send messages, because wires imply copper is the problem. Cables can be copper or fiber. So Internet Protocol to figure out how to send messages through those cables to get messages from point A to point B, but in a very unreliable way. The Internet Protocol will drop your packets, and it will not care. Those packets get lost. So we have TCP, which is going to get add reliability to the internet, and this is handled at the endpoints. So the Internet Protocol, as the name implies, is how the internet itself works, and it's the only way the internet works. TCP is handled by the endpoints. So when you connect to a web server, that server and your machine, those are both speaking TCP, It'll send IP packets through the internet, but the contents of those IP packets will be using TCP. So if one of those endpoints says, hey, you were supposed to send me 500 packets, but I'm missing sequence packet with sequence number 103, can you resend that one to me? They're going to be able to do that with extra IP packets, but being able to detect that a packet was dropped and then request the resend. Thanks, Shads. What is unreliable network looks like? It looks like every network ever. Every single network's unreliable. Since it's all caps, I assume that was a joke, but every single network is unreliable. It's up to our devices to implement TCP and make them reliable communication over unreliable networks. Yes?
Is there anything stopping the road router with an internet protocol from like changing the header maliciously to change some of those recipients?
No. So the question is there anything stopping a rogue router from just like changing IP headers? And no, not really. Just that the companies wouldn't want the negative press and they want their stuff to work is the only real reason. But there might be one employee at a company, they might want to do that for whatever reason. But luckily, that's something where we have TCP, where if a router is doing some malicious stuff, hopefully we can detect that with TCP. If the packet never gets to its destination, TCP is going to figure that out and request resends until it finds a path that avoids that router, just probably by chance. And if the contents are corrupted or whatever, hopefully we'll be able to detect that too. With HTTPS, it's hard to really mess with stuff. It can mess with the headers, but if it messes with the content at all, it won't decrypt properly, which will be pretty easy to detect at least. But yeah, there's nothing really stopping anything. Any rogue routers from doing that. So that's how we're getting reliable communication over the internet. Yeah.
How does TCP know how many packets are supposed to be sent?
That'll be the first message that's sent. So we get reliable communication over an unreliable network. So for our purposes in this course, we're going to assume all of this just works. And we're going to use libraries for all of this. We're going to use our TCP server libraries, and that's going to take care of all three of the, because obviously we're not laying cables. IP is just how the internet works, and then TCP is going to be handled by a Python library that we're just going to import and do it for us. So we start with the assumption that we can reliably communicate over the internet. And then the question is, well, what are we going to do? HTTP. All semester, we're going to talk about HTTP at length, in depth. We're going to use it for everything. HTTP, the Hypertext Transmission Protocol. So what we're going to actually send over TCP will be HTTP requests and responses. So when we actually send a packet over the internet, it's going to look something like this. The first bytes of that packet are going to be the IP headers. The next bytes are going to be the TCP headers. And then the actual payload is going to be the HTTP headers. And if we're sending any message with that HTTP request or response, then some actual content like HTML, CSS, JavaScript, images, all the stuff that we actually want to access on the internet is going to go under 3 layers of headers. By the time and by that I mean in your code, when you actually get a hold of bytes in your code, the IP and TCP headers are going to be gone. Those already did their job. Other code on your machine already read those, did what they were supposed to do, and stripped those headers off. And you're going to get the HTTP headers and content, and that's what you're going to have to start coding. Which means we have to figure out what HTTP is. So HTTP, if you ever want to know anything about HTTP, I can't highlight that, but I'm trying to highlight it. It's in RFC 2616. Absolutely anything you want to know about HTTP, it's in there. If it's not in there, it's not HTTP. This is the RFC, which is a request for comments that's managed by the IETF, and they're the organization that adopts these, adopts these RFCs to be standardized internet protocols, not to be confused with IP, the internet protocol, but protocols related to the internet. RFC 2616 is the document that defines HTTP, at least HTTP version 1.1, which is the one we'll use in this class. So any questions you have about HTTP, it's answered in there. And that is the be-all, end-all. If I happen to say something, I don't think I have any mistakes in here, but if I go off the cuff and start trying to make something up, and what I say doesn't agree with the protocol wins. RFC 2616 wins. That's going to be the answer. Even if I have something in a homework description that says, it works like this. If it doesn't actually work like that according to the protocol, I'm wrong. If you go by the protocol, you're going to be right. And then you should argue, especially if you lose points for that, you should argue with me and get your points. Been doing this class a while. I don't think I have anything that's outright contradictory to the RFC at this point. But the RFC is king. RFC is king over browsers too. I swear there's a bug in Firefox that drives us all nuts in this class. We had to do a very specific thing to get around it. I maintain that Firefox is not compliant with the RFC, but whenever I try to dig into it, I always hit dead ends, trying to figure out where in their code they have it implemented. But RFC 2616, it's linked from the course website too. It's a very large technical document, so it's as dry as you would expect. But especially if you have a very specific question on your homework about how you should be parsing or how you should be handling something that I didn't cover in detail in class, that's your answer. Your answer will be in that document. And I say that, I spend so long saying that because especially outside of this class, bless you, you go out there, you're a web developer and you have a question, you refer to the official documentation. There will be an RFC for most of the protocols that we're going to cover in this class. Go to the RFC. That's the standard. That's the answer. That's where all these protocols are defined. There's an RFC for IP, for TCP. If you're writing code to implement any of these protocols, the answers are going to be in the RFCs. Okay, hypertext transfer. Oh, I said transmission, didn't I? Transfer protocol. The acronym kind of, I don't know, it's a little outdated, I guess, but it's fine. We're going to stick with it forever. Hypertext means text that can refer to other text, which we know these days is just links. You can click on a link. That was a very new fundamental idea when the internet first came out, when HTTP first existed. Now we have a protocol to transfer text that has links to other text, and then you can click around to browse the internet. That was, at one point, was a brand new idea, and that's where the namesake of the protocol comes from. This idea that we can have hypertext. Before the internet, all text was just text. It was printed. You couldn't click on a book. So that was a brand new revolutionary thing that's just second nature. It's like air these days to us. But that was new at one point. And in this course, we're always going to use TCP to transmit HTTP messages. I say almost always. There's other protocols. Google's always coming out with new protocols that tries to be fancier and faster and all that stuff. But we're going to always use TCP, and almost always at this point in the internet, it's going to be TCP. Which is why, of course, we introduced TCP on day one. So HTTP is a protocol. I've been using that word a bit, just a brief definition of protocols. It's just an agreed upon set of rules. And this is probably the second thing I would say where I'm dispelling the magic of the internet. There's no magic here when we're sending messages, like how those messages are structured or anything. It's not magic. It's just we agree on protocols. So IP, for example, the headers are in a specific order. I very briefly showed that the protocol for IP headers on the screen. What that defines is when a router on the internet or an end device gets an IP packet, the first few bytes, didn't I? No, I didn't. The first few bytes are going to represent a certain value. The first thing for an IP packet is the version of IP that's being used. And then, some other values, I don't memorize them all. Then the certain byte numbers in that sequence are going to be the source IP and then the destination IP. All the protocol is doing is saying, when you get a whole bunch of ones and zeros over the internet, read them in this order. The first ones and zeros mean this. That's where I'm going to put the version number. These ones and zeros are going to mean this. And we just all agree that when I write code to send an IP packet and you write code that receives an IP packet, and all you can see are ones and zeros over the internet, this is what those ones and zeros are going to mean. I'm going to send them in this order, and that's what they're going to be. If we all agree on the protocol, then we can make sense of those ones and zeros. But there's no magic. It's just ones and zeros going through the air, going through the cables, and then we have protocols to make sense of the ones and zeros. So HTTP, just like all the other ones, it's an agreed set of rules. If web browsers and the web servers that we write, if we're both reading the same RFC and we're implementing all our code the same way, we can effectively communicate over HTTP. But all we're doing is making sense of the ones and zeros. We're going to get the payload of TCP messages. It's going to be bytes, just ones and zeros in groups of 8. And we're going to use the HTTP protocol to make sense of those ones and zeros. If we code the same way that the browsers are expecting, we can effectively communicate. HTTP is a request-response protocol, which means our server is going to get a request and then respond with a response. It's going to be a one-and-done thing. There's no persistent connection. Like there is with TCP. TCP is a connection. We send a bunch of messages back and forth. HTTP is one request, one response, done. We can't talk to a... do I introduce clients? Yeah, I do. So we have a client and a server. And by the way, from here on out, whenever I say server, I'm going to mean software, the software side of server. I showed the picture with a server room earlier, the hardware type of server. I'm never going to mean that unless I explicitly say so in this class. I always mean software, which can run on any device, but that you'll run on your laptop. What's the current version of HTTP? It's not really a current version. Like 1.1 is still used extensively throughout the entire internet. There is HTTP 2.0. There's the aforementioned, the ones that Google's coming up with, Quick, I think. And I think Quick got relabeled as 2.0. I forget how it all works. But there are a few other like fancier protocols. Most of the protocols beyond 1.1 are designed for efficiency. Just sending messages faster back and forth. They're made to reuse TCP connections, which 1.1 can do anyway. And then some of the newer ones are designed to have make encryption faster. Not really faster, but to I forget the details. But it's trying to get fewer round trips from client to server, as few as possible, and be able to send messages without having to open up new connections, especially if those connections have to be encrypted. There's a lot of back and forth to negotiate an encrypted connection over the internet, and we want everything to be encrypted these days. So the newer protocols are trying to bundle that together to get a quicker connection. That's why some of them can, I think they are starting to replace TCP because they're just rolling that all into one big protocol with fewer round trips to establish a connection. Some of that might be wrong. I don't know 100% about those. But at the end, when they're actually doing the work of the internet, they still behave very similar to 1.1. So there's really no reason to dive into those ones because everything you learn in this class, it's going to transfer over to those other ones anyway. So I don't see a need to dive into the extra complexity to get a little bit more efficiency. But when you're Google and you're handling trillions of requests per second, I don't know what the actual number is, any little bit of efficiency they can squeeze out of their protocols, even if they have to develop their own, they're going to do that because it's worthwhile for them. In what CSE 3.12, you're not going to care about saving a nanosecond. Or I shouldn't say that. Saving hundreds of milliseconds. It is on a higher level than nanoseconds, but we're not going to be concerned with that. So it's a request-response protocol. And to serve one single page, this is always a source of confusion. I'll try to hopefully clear the air today pretty well. But you usually need many requests to load a single web page. If you go to a web page and you go to your browser console, don't worry if you haven't ever heard what that is. I'll show plenty of demos throughout the lecture. shown the console. But you'll be able to see all of the HTTP requests that are required to load one single page. It's going to be lots. For any modern web page, there's lots of requests. You're going to need one request to get the HTML. Typically, a typical web page goes, you request the home page, you get the HTML. That HTML has links to lots of other resources, namely CSS, JavaScript, and any multimedia that's to be loaded on that page. And then it makes requests for each one of those separate resources independently. HTTP is a request response protocol. So the client's going to say, give me your HTML, gets the HTML, reads it, and says, whoa, I need CSS. Goes back to that web server and says, hey, I need your CSS file. Server says, here's the CSS in a response. It says, hey, I need your JavaScript. Here's the JavaScript in a response. Hey, I need this one image. Here's that image as a response. Each one of these are separate request responses from the server, which means when you're coding a web server, you have no concept in that web server of loading an entire web page. That doesn't really exist in a web server, which means it won't exist in your homework when you're having your server host an entire web page. You don't actually host an entire web page. You host the HTML, you host the CSS, you host the JavaScript, you host your images, all separately with separate requests. And then it's up to the client to make all the requests that it needs for your web page and then mash them all together in the browser. You and your code will not have any concept of how all those pieces go together. You're just going to serve all those files and let the client figure it out. I'll get that question. I'll still get that question this semester, but because it is confusing when you're writing it, like, how does this, it just seems to work, like, and usually when it doesn't work, like, how does this work? I have these separate files that I'm hosting. So web server, I already harped on this more than I usually do in previous semesters, so I don't need this slide so much, but web server is the software that speaks HTTP. So I am talking about software that's running, that's listening for TCP connections and expecting HTTP requests over those connections and then responding with HTTP responses. Front end and back end is new. I haven't really talked about this much this semester. So let's talk about this. Front end and back end, there's two sides to any web app. I have to be careful with that. Web pages, there can just be a front end, that's fine. When it's a web app, that's where you have a server and communication with the front end and back end. That's why this is web applications, not web pages, I forget what else I was considering calling this, but web apps is the more appropriate term. Web apps, when you have a front end and back end communicating with each other. The front end of a web app is anything that runs on your client's machine. This is all of the stuff that you're sending your client and they're running on their device. This includes all your HTML, CSS, and JavaScript. All that put together builds the functionality of your page. Then you also have the multimedia that you want to display to the user. That's everything on their machine. So anything that runs on your computer as you're visiting a website, that's the front end. The front end is going to make HTTP requests to the back end or the server. I'll usually call the back end the server. The back end is the server, and that's all of the code that you write that you never send the client. So all of your server code that's handling requests, that's talking to your database, that's authenticating users, all that sensitive stuff that you don't send your user, that only happens on your server, that's the back end. And your back end is going to listen for those HTTP requests from the front end and respond with HTTP responses. But when you build a web app, you're going to build the front end and back end and then decide how your front end and back end are going to communicate to deliver the final user experience. And it looks something like this. You're welcome for saying bless you. I used to not do that, but I'm like, why am I being so rude? I'm going to say bless you when people sneeze. The front end and back end, so this is the client, which I usually say client. It's almost always going to be a browser in our cases. Sometimes it won't be. So I'll say client. If you think browser, at least for the early stages of the semester, that's fine. But the browser is going to send a request for the HTML from your server. It's going to get the HTML, read through the HTML, say, whoa, this HTML says I need some CSS, some JavaScript, 6 images, and a WebSocket connection. it's going to send all of those requests as separate individual requests to your server. So from your server's perspective, you got a request for the HTML, a request for your CSS, a request for your JavaScript, a request for your image, with no care in the world that those 4 requests came from the same user. You don't even care that it came from the same user. They might have been 4 separate users that only wanted one portion of what you're hosting. Your web server does not care. You're just going to send, every time you get a request for anything, you're just going to respond with a response containing whatever was requested. Then it's up to the browser to make all the right requests and then render all of that together and actually render your web page or the front end of your web app. I would call that a web page at that point, excluding the back end. Everything that you send them is going to be that page. Okay, there's different types of HTTP requests. Oh, I say post. I meant to remove this. We're only going to worry about get for now for homework 1. Then homework 2, we're going to worry about post, put, and delete. I'm missing one there. Update. I missed an update. Or no, that's put. Yeah. I mean, this isn't a comprehensive list anyway, but this is a list of, I think it's comprehensive of what I'm going to have you do on homework assignments. Not completely comprehensive for the protocol, though. But to start, we're only going to worry about GET requests. But there are other ones. I don't want to give an overview. I want to get a little caught up here on time. But GET, as the name implies, when you're getting information from the server, I'll briefly introduce posts, but we'll save the other ones for homework 2 content. So GET is whenever you're asking a web server for information, you're going to send them a GET request. I put these typicallys here because people can use the protocol in weird ways, and the protocol technically doesn't stop them, but you should not have any body to a GET request. There should only be a URL and HTTP headers. We're going to look at both of those in the next few slides. And whenever you say click a link or download anything, you're sending GET requests typically to get content. If you want to send content to a website, you're going to use a post request. Post request, in addition to the URL and the headers, you're going to have a body to the request which contains anything in the world. Could be anything. That's where HTTP really opens up and we can do anything with the protocol. But first we got to figure out what HTTP headers are and how URLs play into the whole thing. So a URL, you've probably seen these, you've seen these before. You've seen URLs, but let's break apart the structure of a URL because you might not have thought too much about what they are. So this is the structure of a URL. These are all the parts of it. Protocol, most of these will be really important. I'll briefly talk about query string and fragment, but I don't think I want to use them this semester. I feel like they're always a detraction from the important content I want to cover. But the protocol, what protocol we're going to use? For starters, we're always going to see HTTP here. So HTTP : host and port. Usually you don't see the port on a URL because you'll use the default port. If you're using HTTP, the port is automatically 80 unless you specify the port. If you're using HTTPS, the port's 443 unless you specify the port. For the homework, we're going to specify host and port, and you're going to run your apps on port 8080, so we do need to know this part of the protocol. Host and port. Usually host is a domain name, but it can be an IP address as well. Port, whatever port number you want to connect to, if you want to override the default. / whatever path you want to request. Question mark as a special character, query string, and then hashtag fragment, which used to be $, but we've renamed that symbol, I suppose. The query string, everything, this question mark and forward is optional. So if there's no question mark or hashtag in your URL, that means you don't have any query string or fragment. So most of the URLs, if not all this semester, that's how we're going to see it. It's just going to be /path and then cut it off there. But query string, if we want to have additional parameters, like if you do a web search on the internet, you'll see a query string. When you type in the search box and click go, it's actually going to create a URL with your search embedded as a query string and send that to the server to get your query out there. And fragment, if you want a specific portion of a website, usually used for navigation. For example, if you want to send somebody a very large Wikipedia article but there's one section in particular you are interested in, you can send them a fragment which says, go to this page, but scroll down to definition. When they click this link, it'll go, I might as well give a demonstration, of course. Give a demonstration of it. So when this loads, of course it's not gonna, of course it didn't work. But it should have scrolled down to, I don't know why that didn't work, and I'm not gonna stress about it. Oops. I'm not gonna stress about it. Here we go. I'm not gonna stress about it, but it should jump down to the section that you're referencing with the fragment. I think that didn't work last semester, and I forgot to fix it also. So HTTP is stateless. So this is what I mean when you get those 4 requests. They happen to all be from the same user requesting your one website. You don't care that those 4 requests came from the same user. They could have been from 4 separate users or all the same user. Doesn't matter. Don't care. HTTP is completely stateless. It doesn't remember anything about a transaction. It gets a request. The request is self-contained. You only have that request, no extra information like, oh, this person just requested the HTML, so this request, I probably want to put some extra stuff on this. No, it's you get a request. Whatever's in the request, that's all you have to work with. And then you use that request to send the response, and that's it. Nothing else. Usually we want to override this to an extent. We can add cookies, which we'll talk about next week or week 3. I forget where I put it. But you can get some kind of pseudo state, but the protocol itself is stateless. So we get a request, we send a response, and that's it. Any new line in HTTP is going to be a CRLF or a /r/n. This is very important throughout the entire semester. It's probably the first mistake anyone will make. If you do make the mistake, this will be your first one. I worded that wrong. If you make this mistake, it'll be the first mistake you make in the course because it's like the first thing we do. But new line characters, new lines in HTTP /r/n. Normally, you would just have the /n there, right? And in any programming language, you just have the /n for a new line. We need a CRLF, carriage return line feed. This is back from the days of printers when you would get to the end of a line on a physical printer. You would have the ink and the heads slamming into your paper, and you would get this carriage to the end of the paper. You would, in 2 steps, get to the next line. You would return the carriage back to the left of the page, and then do your line feed, which would be to get your paper onto the next line, and then continue. So you would have a carriage return, and in computer terms, move the cursor to the beginning of the line, and then go down to the next line. So it's an old-fashioned thing, but we're stuck with it. It's part of the protocol. We're not going to update the entire internet to get rid of those /r's. So /r/n or CRLF, if you hear me say either of those things, I mean a new line character in the HTTP protocol. And it has to be that. It has to be that way. So when you're parsing HTTP requests, be aware of this. Know that /r is there. If you split on /n, for example, you have a trailing /r at the end of every one of your lines. And when you're preparing your responses, sending a response to the browser, make sure you have your /r's there. Because if you don't, the browser may or may not understand the response, and your page might not render properly. /r/n. All right, so let's finally see some of these things in action. Did the fragment link example not work because there's no section in the table of contents called? Oh yeah, I think Wikipedia updated maybe just that article, if not the way they do things. That might be it. They might have renamed that section. Why would you need a new line in an HTTP request? Good question. Let's talk about what HTTP requests are. So let's look at a GET request. So here's a GET request, a simplified one. When you start seeing real GET requests, there will be a lot of extra stuff that your browser adds. I trimmed this one down pretty small. So this is a request for CSE312.com's homepage. This is what my server is going to see, roughly speaking, when you visit the home page. So let's pick this apart and talk about what it is. So I have new line characters. I have content on new lines. That's where we're going to use the new lines to answer the question in chat. And this is actually going to look like this. So this is more accurately what it's going to look like. In the slide, I'll replace the /r/ns with actual new line characters because we're humans, not machines. But when you're writing your code, this is what that request is going to look like. We're going to have this first line and then a /r/n for the new line character, the next line /r/n for the new line character. And note way at the end here, that wasn't a typo on my previous slide, we do have a blank line at the end. /r/n for a new line, and then right away another /r/n to say the end of that line. So it's a blank line at the end of the request. That needs to be there. If that's not there, things break and your page won't load. That needs to be there. And we'll explain why when we get through this, but let's start from the top and go piece by piece. So this blank line is very meaningful right here. That's a /r/n /r/n to get that blank line in there. All right, so the first line of a request, and this is what you're going to see. This is what browsers are going to send your server. This is what you're going to get, what you have to parse. The first thing you do on homework 1 is parsing these requests. This is the format you'll have to follow. The first line that's sent is going to be the request line. This is going to have 3 values separated by spaces. The first value is going to be the method type. For our purposes in homework 1, it's always going to be get, capital G, capital E, capital T. Then a space. There's a little hard to see, but there's a space right here. The second value is going to be the path. This is everything after the port number in the URL. So if there are query strings and fragments, that's going to be included in the path. So it's not, strictly speaking, just the path, but it's everything path and after in the URL. So that path of the URL goes here. And then the HTTP version, for purposes of this course, it'll always be HTTP/1.1. So that's the request line. So the first thing you're going to do when you're parsing these things, look for your first /r/n. Everything before that, split it on spaces. These 3 values cannot contain spaces, which implies in your URLs you cannot have spaces in the path. In fact, can't have spaces anywhere in a URL because it would break our parsing code here. It's part of the HTTP protocol. Can't have spaces here. So split on spaces, you should get 3 values every single time. And the most important thing, especially for homework 1, when you can guess what the first and third values are because they're always going to be the same. But for homework 1, the most important thing is getting this path value and figuring out what the hell is even being requested. What is this user requesting? What's that path? Are headers expected to have spaces before the text? Good question. Maybe. So this space before the text, well, let me get on the next slide anyway, where I talk about, I don't talk about headers yet. So let me answer the question quick. This space after the colon and before the first character of the value of a header is optional. The RFC 2616 says if that space is there, it should be removed when you're parsing. And if that space isn't there, that's perfectly fine too. So this space can be there or not. It's almost always there. In all the major browsers, I always see this space. But that space should be ignored by your parser. So when you split, if you're splitting on colon, you need to strip out this white space. That white space can be there, but it's just there for no meaningful purpose. It doesn't mean the values start with a space. It's just there for, I don't know, aesthetics, I guess. I don't know why it's there. But it can or can't be there. Your parser should remove it if it exists. And that path will be anything in the anything that was requested in that URL. So this would be a request for the home page. It's just a request for / or the root path. Typically, this is where you're going to serve your HTML, your home page HTML at /. And then if a more specific thing is being requested, that's going to go right in that request line. If you're requesting this slide deck, you're going to send an HTTP request with this as the request line, request for these exact slides. So in your server code, you're going to check that path to see what's being requested. And then the headers. So headers are key value pairs. There can be any number of headers, and this is the bulk of the work for Learning Objective 1 on Homework 1 is parsing these headers. So any number of headers separated by /r/n, name of the header, colon, and then the value of the header. You do need to be a little careful. I know I said on the previous slide, when you're splitting on colons, then handle the space. But the values themselves can contain colons. So splitting on colons is probably going to, has the chance of destroying your data. So look for the first instance of a colon and then grab everything after that as the value. But it's name, value, name of the header, value of the header, separated by a colon and an optional space. If the space is there, you need to strip it out. If it's not there, then you don't have any extra steps to do. Well, you'll still run your strip and your code to do that, but yeah.
So is this optional space always only just one, or there be like multiple?
I don't know exactly. I would guess there could be multiple, but if you call, we have to use Python, so I can give specifics here. Call .strip on it, and then you won't have to worry about it. It removes all leading and trailing space. As long as you're calling .strip on the values of your headers, you won't have to worry about it. But in practice, I've always seen it as one single space, and I don't think I've ever seen a browser that wouldn't have that space there. Oh, yeah, I forgot. I even expanded on this bullet point. I added that this morning. Don't forget to do that. It'll cause not just bugs, but bugs that are very hard to find. I think you would get away with it in Homework 1, but later on in the course, if you're not stripping out that space, oh my goodness. I've seen like Homework 2, 3, even 4, really strange bugs in office hours, and that was the issue. They weren't stripping out that white space. Specifically with WebSockets, it caused a lot of issues trying to do the WebSocket handshake. Bless you. And then responses. So we get our request. We're going to parse. It's a GET request, so it's going to end in /r/n/r/n. We have the request line and all the headers, and then that's going to tell us everything we need to know to be able to handle that request. So when we parse that request and get all the information out of it, our goal is then to send an HTTP response back to the user. So we want to send something back that's going to look like this. Luckily for us, requests and responses have very, very similar structure and similar format, but there are some key differences I got to highlight here. So if we send this response to the client, this is going to display hello in their browser. That would be the effect that we would have here. More accurately, it's going to look like this. You're going to have those /r/n's in there. And I'm going to copy this at this point. I don't know if we'll have time to do the demo, but I'll use that as part of my demo if we get there. We ain't going to get there. So let's pick this apart and talk about each part of this. So we have the status line, very similar to the request line, but with some key differences here. The order of the values are different. Well, actually, the values are just different. Let me just talk about it. The version, HTTP version, comes first instead of last here. It's always going to be HTTP 1.1. So every single response you send for this semester, every HTTP response will always start with these characters, HTTP/1.1 space. Then space separated. So space, and then the response code or status code, and status message, which is reason phrase in the RFC. I don't like reason phrase. I think that sounds weird, so I'm going to call it status message. Response code and status message. I should probably update this to response code since that's what I'm calling it. Separated by spaces. And the status message actually can have spaces in it for what it's worth. So you don't have to have exactly 2 spaces in this line. The response code can be space separated. So the parsers in the browser are going to look for the first 2 spaces, and everything after the second space is the status message or the response message. I use way too many different names for those things. The response codes, I call them response codes right here. Status code, and then I call them response codes. I mean the same thing when I say that. So the response code, I won't go over all the response codes. As we need them, we'll introduce more and more. But they do go in levels. So 200 level code, any response code that starts with a 2, this means everything went great. 200 is the most common response code out there. It just means Everything went good. Okay, everything's good. This is whenever you visit a web page and everything's just going great. You're going to get a bunch of 200 responses. 300 level codes means there's a redirect that you requested something and it's the server wants to redirect you to something else, some other URL. It's going to send you a 300 level code for whatever reason. If the site moved, if they changed domain names or something, they're going to send you a 300 level response. Or for whatever reason they want to redirect you. We're going to use that in homework 2 for some login redirects to redirect to the login page, things like that. 400, this means something went wrong and it was the client's fault. 404 is our most common error code that we see when using the internet. And 500 level codes, something went wrong and it's the server's issue and there's some dev that's going to get a phone call and they're going to have to, sleeping, whatever they're doing, they got to wake up and fix that. This is the stuff of nightmares for web developers. I hate seeing 500 level errors. And the message is a human readable version of the code. The browser doesn't actually care about these messages. You can actually type whatever the hell you want right here and nothing's going to break, but eventually probably another dev is going to get mad at you at some point. But these codes do have meaning to the browser, so the browser is going to need these codes to be accurate. Which database are we using with our Docker Compose file? Ooh, good question. Good question. So in the past, I've allowed MySQL and MongoDB. Going with my shift to requiring Python, I might require MongoDB. I don't know. I don't know if I have to go that far. If y'all want to use MySQL, I probably won't stop you. But MySQL, it has some extra pain points that MongoDB doesn't have. So anybody who chooses that does run into specific issues. But if I'll give that warning, I'll probably let you do it and give you that warning. And then in office hours, if you have those issues, I'll be like, why didn't you just use MongoDB? But if you know how to use MySQL and understand how to avoid those pain points, then I probably won't stop you. I'll probably leave it up to either of those two. Yeah, would I care? If you want to use some other than those, let me know. I don't think I'll be too picky about those. If you want to use Postgres, for example, I don't think I'll be too picky. When you send a response, you have to, we're at 3:49 already. I'm almost at the end, but I don't want to rush it. I need to give you time to do the lecture questions, so we'll save the next few things for next time.